In this lecture, we'll try to explain a very important concept in time series econometrics, and that is the concept of white noise. Now, white noise is basically, we can understand this concept by comparing with the error term that we have come across in ordinary least square when we deal with cross-sectional data. Okay, and we'll try to understand white noise as a comparison of the error term in ordinary least square. To define white noise, I mean, we can say white noise is a type of time series only with certain specific properties, okay? And the main use of white noise is basically to understand, when your model is plausibly the best fit. So you probably don't see any more trend or, pattern existing in the error term. So it is basically an error term, which is the distribution of the error term is without any pattern, right? And that is what we actually do when we deal with the error term in ordinary square regression. So when we actually use the error term, basically the whole purpose of analyzing the error term is to understand if there is any existing pattern in the error term. And if, say, there is any pattern that you see in the error term, that means your model is not yet the best fit. So something else is still being captured by the error term, which is supposed to be in your model, right? And that is why you uh, actually when you look at the Gauss-Markov assumption is all about that your error term would actually be free from all these different trends or patterns, right? And we actually use several properties in Gauss-Markov assumptions which are actually dealing with this. So one is that zero conditional mean of error, right? And which is nothing but, if I just write it down here, just a second. Give me a moment. Okay. So if I write it here, so it is basically uh, expectation of ui given all the xi. Sorry for my bad handwriting here. It's really a little not so much in control, it seems. Equal to 0, right? So this is zero conditional mean of error term. Okay, that's basically 0. And zero conditional mean of error term is really important because that is a fundamental assumption that your errors, if you sum it up for any given x, it will be basically 0, right? Basically take a mean, it will be basically 0, okay? Now, the other properties that we have seen when we dealt with cross-sectional data is that we wanted to have the error term to be homoscedastic, where your the variance is something constant. You don't really want a variance to be changing, right? So if you have a non-constant variance of the error terms, what will happen is, as you increase the value, your error terms will have a some sort of you can see some the variance is increasing or variance is decreasing. So that is something you don't want. You want a constant sort of variance. The third thing you saw in, and this property is called homoscedasticity. Let me just write it down. Homoscedasticity. Let's see. CT, homoscedasticity. So we've done, but what it means is a constant error term. And the third one was there should not be any autocorrelation, which means among the error terms, which means that if I take a covariance of the error term, say I and EJ, so what we will have is it should be equal to 0. Okay. So these were some of the tests that we were doing using Gauss-Markov assumption when you're trying to understand if the error term is actually free of any sort of pattern, right? And So that is about the cross-section data, and what we precisely do in case of time series data, we want to get an error term, something similar that will tell us the model is already well fit. And to do that, we again have some properties that we need to fulfill. Now, I would want you to actually pause the video here and think about the properties that it should have in case of time series, the properties the error term has, which would make the model that you fit is the best model, plausibly the best model. Okay, so you need to think through, or you need to basically write down what are the properties you can think of, and I'll come back just in a while. All right, so hope you have thought through it. So let me just again, like let us just intuitively think about it. Okay. So for a time series, what we'll have of the error terms, if suppose the error terms are the mean is not zero, so that what will happen is, so mean is actually there is some value in the mean which is not actually captured in the your original model, right? So that is something you do not want. Standard deviation, against, if your standard deviation is not constant, so what will happen is that your it will actually vary from time period to time period. So that means there are certain pattern that your model is again not able to capture. And the third, just like what you have seen in case of cross-sectional data, third you want uh, the correlation between the error terms to be zero. And what you call here for time series data is the lags, right? So correlation between lags. So if you take the covariance uh, for different data points with lag, so it should be zero for your white noise. Now what I'm going to do is I'm just going to write down these properties. So one is that mean has to be zero, has to be zero. Then you should have your sigma square constant, and then curve, here I will write ET instead of EI because it's the time series data, and I'll write ET say minus 1 equal to 0. Okay, so that's basically the same, similar set of properties that we need to have for time series data. All right, so now let me actually draw it. Let me actually try to understand visually, time series, which is a white noise time series. So as you understand, so white noise is basically a time series with certain specific properties, and these are the properties. These are the properties, sorry. These are the properties. These three are the properties. It's very tough to actually. These three are the properties, okay? All right. So now we are actually going to visualize a white noise time series, all right? So let us just try to draw what a white noise time series would look like and what it should not look like. So let me draw this one. Let me just change the color a bit and let me draw it here. Okay. Say it looks like, oops, it looks something like this. Okay, it's more like a sine or cosine curve. Okay, something like this. Now I draw another such curve. Where I have a time series like this. Sorry, this is absolute. Okay, and then I draw another one. Okay, let me just first explain this one, then I'll go to the next uh, curve. Okay, so this one you see the error term in each period is somewhat like they're all related. Okay, it's just gradually coming down and then it's gradually coming up again, it's gradually coming down. So here we have actually these are the error terms and this is your time. Okay, so here also the same thing, error terms and this is your time. Right, now they are all actually related. You see that the if you know the error of certain time, you can actually decide what is going to be the error in the next period, or similarly here you can also say something. So which property of white noise is being violated? Can you make a guess? So the property that is going to be violated is this curve of Et and Et minus 1 is not equal to 0 here. Is not equal to 0 here. Now, for the second one, can you tell us which of the property of the white noise is not being followed? So here, what is happening is if you see the sigma square, the variation in the distribution is suddenly like spiking up, and then again it's pretty like constant. So if I just try to say divide in different time periods, so this one, and then I draw this part. Then I draw say this part, then I draw this part, okay, then I draw this part. So all these different time periods, you will see the variance will actually be different. So for the first period, the T1, we will have pretty like average variance, whereas in T2, what you are going to see, the variance will increase a lot. T3, variance is pretty much like constant. P4, again variance is constant. P5, there is a high variance. Okay, or yeah. So basically, variances different periods are going to be different. So how I can write it? You can basically write it as the sigma square not equal to C here. So this property is being violated. So then we can draw something like a white noise. Let me just erase it. Just erase everything. So we can draw, say, white noise, like something. It should be something like this. So it will have. So let me change the color again. So it will have. Say the mean is constant, and it should be random. So you are not really able to predict what is going to, you know, be the next error term given. Oops, this one is wrong. So what is going to be the error in one period given the previous error? Okay, so that should be something like your white noise. All right. So we learn more about white noise and how do we really measure it. We learn some mathematical techniques, some graphs of plotting white noise. But the idea behind white noise is this. Okay. So now the last point about white noise. Why is it called white noise? Okay. Why is it not called blue noise or pink noise? So it has come from the analogy of with the analogy of light. So when you mix all the different colors, so it will lead to white, right? So it is basically a mixture of all color, and the frequencies enter equally. So basically, white noise is like something like all the noise are mixed up, and you really can't get any pattern out of it. So that's basically the idea. Okay. So basically, to summarize, white noise is a type of time series. It has certain properties. It is specifically used to understand when your model is plausibly the best fit, and it has tremendous use in time series. Okay, so with this we end this lecture here.